In today's session, we will discuss some of the most important and frequently asked questions on the BJT and associated circuits like biasing techniques, common emitter, common base configurations, and amplifier analysis. All these question models are based on the previous year examinations of GATE, IES, ISRO, DRDO, Polytechnic Lecturers, and other state public sector unit examinations. Let's welcome to the channel Electronics Pariksha. So next question, the addition of emitter resistor to the DC bias of the BJT dash the stability of the circuit. So if you see the circuit diagram, we'll see this in great detail. He's asking for emitter resistance. Emitter resistance will come into the picture in the self bias. So this is a common emitter configuration where emitter resistance is added in the circuit along with the R1 and R2. That is, this is VCC, this is collector resistance RC, this is output resistance, coupling resistance CC, this is input capacitor Cin for input voltage. There will be a capacitor across the emitter resistor. Okay, this is the basic circuit. The voltage across this R2 is nothing but VB, that is nothing but base voltage that appears across the base of the transistor. And there will be a current flowing I1. The same current flows through R2 also. R1 and R2 has the same current, that is I1. Because the base current is treated as negligible current here. At this junction, there will be a base current, but that is negligible. So we assume that the same current flows through R1 and R2, like this, same current flows. This is the collector current IC, and there is an emitter current IE. This is the basic circuit. So in order to analyze the stability, we have to convert this diagram into the Thevenin's diagram. The Thevenin's equivalent diagram will be like this. This is the V Thevenin's, and there will be R Thevenin's. And this is given to the common emitter. The remaining diagram remains same. Okay, only the input part we are converting into the Thevenin's equivalent circuit for simplification purpose. Like the video, share the video, and subscribe to the channel for better content and more videos. This is the circuit, and there is a current that is flowing through emitter resistance, and this is VB, base emitter voltage. If you apply the Kirchhoff voltage law in this loop, we'll get V Thevenin's is equals to the current IB multiplied by R Thevenin's plus VBE plus IE into RE. This is the equation. So if you write this, IB into R Thevenin's plus VBE plus the emitter current can be written as base current, sum of the base current and collector currents. So emitter current is basically sum of the base and collector currents. So on the other hand, if you see the stability factor, S is equals to 1 plus beta divided by 1 minus beta DIB by DIC. This is the formula for stability factor. Now we need to find out the DIB by DIC here. So by differentiating this equation, by differentiating the above equation with the DIB, this is equation 1. You are differentiating equation 1 with DIC. You will get like this. The V Thevenin's is constant, so it will be 0. Here IB turns into DIB by DIC, and here is also there is a DIB, so I am writing these two parameters together. So R Thevenin's plus RE plus here IC, that remains, the differentiation of IC by IC is 1, so RE. So we'll get DIB by DIC is equals to minus RE divided by R Thevenin's plus RE. By substituting this in the stability factor equation, we will get stability factor S is equals to 1 plus beta by 1 plus beta RE divided by R Thevenin's plus RE, which can also be written as S is equals to 1 plus beta divided by, here in a simple way, instead of writing like this, you can mention this is the final stability factor equation. If circuit is designed in such a way that the Thevenin's equivalent circuit is far lesser than emitter resistance, means at least 10 times, the Thevenin's equivalent circuit is at least 10 times lesser than emitter resistance, S can be approximately equal to 1. So lower the value of S, higher the stability is. Lower value means higher stability. So we are improving the stability here. One more thing is, here the stability can be approximated to 1 when R Thevenin's is lesser than RE. But what is the stability factor without RE? That we need to find out. What is the stability factor? What is stability factor without Re? That is without emitter resistance. Means Re must be equal to 0. So what will be the equation? S is equals to 1 plus beta divided by, it will be, this entire factor will be 0. So it will be 1 plus 0. That is equals to 1 plus beta. Usually beta varies, beta will be in the range of 700. So the stability factor will be in the range of 700, 600 to 700. So here we are getting stability factor approximated to 1. So which is better? This is better. So by adding emitter resistance, we are trying to attain the stability factor S is equals to 1. So it improves the stability of the circuit. It will not degrade, it will affect. It does not affect is also wrong. It will affect destability. That also false. It improves the stability of the circuit. Next, we'll see the configuration of a cascode amplifier is. What is basically the cascode amplifier? The cascode amplifier is designed to reduce the Miller effect. We'll see what it is. Cascode is basically is designed to reduce Miller effect. Miller effect comes into the picture when an amplifier is set to high frequency amplification. When an amplifier is trying to amplify high frequencies, trying to work with high frequencies. Okay, that is the Miller effect. What it is? So this is the common emitter configuration. This is the base, this is emitter, and this is collector. There will be certain capacitances, junction capacitances. We call this as junction capacitance. This is the collector base junction. So there is a junction capacitance VBC. And here is also one more junction capacitance, that is V, that is CBE. This is CBC and this is CBE. So these junction capacitances play important role when the input of the transistor is higher frequency. At the higher frequencies, what happens? At high frequencies, the capacitor CBC acts like a short circuit. Acts like short circuit, and this is the reason for the leakage current. Due to this, there will be a leakage of the current from output terminal to input terminal. From the output collector terminal, the current will leak to input base terminal, because of which the overall input current that is fed to the base of the transistor will reduce drastically. Because of this, the output voltage will fall down. Okay, so at the higher frequencies, the base collector capacitance acts like a short circuit, leading to the fall in the voltage gain, fall in output voltages. That is nothing but voltage gain will reduce. To nullify this effect, means to reduce this Miller effect, we have gone for cascode. So if we place a circuit between the output and input, instead of directly leaving it like that, if you place a device between output and input, then the problem will be resolved. So we are placing CB circuit, common base circuit, between output collector and input base of this CE transistor. So the input stage will be CE and output stage is nothing but CB. If you see, the diagram is like this. This is the common emitter. This is the common base. So between the collector and base of the common emitter configuration, you are putting common base. So input stage is a CE stage, output stage is a CB stage. This is a cascode amplifier. Answer is option B. We'll see the next question. A transistor is operating in active region. Under this condition, junctions of forward bias or reverse bias, she is asking. We'll just see, there are two junctions we know, emitter based junction and collector based junction. What will be the mode of operation if these junctions are, with respect to the biasing of these junctions? If the emitter junction is forward biased and a collector junction is also forward biased, transistor acts in saturation mode. Transistor works in saturation mode, acts as a closed switch. If emitter junction is reverse biased and collector junction is also reverse biased, transistor acts in cutoff mode. So acts like a open switch. If emitter junction is forward biased and collector junction is reverse biased, this is active region. This drives transistor into active region, so it acts like an amplifier. If emitter junction is reverse biased and collector junction is forward biased, this is called inverse active mode. So here he is asking for active region. So the answer is option C. Emitter based junction is forward biased and collector based junction is reverse biased. Like the video, share the video, and subscribe to the channel for better content and more videos. We'll see the next question. The current amplification factor for common base is 0.5. What is the value of base current if emitter current is 1 milliamp? For the common base, for CB, the current amplification factor is alpha. Output current is collector current, input current is emitter current. So here given alpha is 0.5, collector current is not known, we need to find out. Emitter current is 1 milliamp. So here collector current is 0.5 milliamps. We know that emitter current is equals to sum of base and collector currents. So the base current is equals to emitter current minus collector current. That is 1 milliamp minus 0.5 milliamp is equals to 0.5 milliamp. So the base current is also 5 milliamps. Answer is option A. Stability factor of the self-biased circuit is, we have seen the stability factor is equal to stability factor formula 1 plus beta divided by 1 plus beta Re divided by R Thevenin plus Re. This is the formula. Here R Thevenin is nothing but base resistance Rb only, which can be equated. So the stability factor depends on beta, emitter resistance, and base resistance Rb. So answer is option B. We'll see the next problem. For the single stage C amplifier, the current gain AI is minus 49.32. R1 is 1093 ohms. RC collector resistance is 1 kilo ohms. Load resistance is 1.2 kilo ohms. Collector resistance is 1 kilo ohm. Load resistance is 1.2 kilo ohms. Now he's asking to calculate the voltage gain. So when you want to calculate the voltage gain, the transistor basically you have to analyze with the AC load. That is called AC load analysis. While drawing the AC load analysis, the capacitors behave like a short circuit, and DC voltage sources behave like a ground. So the collector resistance RC and RL come in parallel with each other. This is called AC load analysis. At the input side, as the DC sources will be represented with the ground, both R1 and R2 come in parallel with each other. This is in the AC load analysis. This is the input voltage source. Okay. So here if you see in the AC load analysis, DC voltage source will be represented with ground. All capacitors will be represented with short circuit. Okay. Now if you observe carefully, this is the current IC, collector current is flowing like this, and this is the current IB. This is the source current IS. Okay. Now the output voltage is taken here, the input voltage is here. This is the input voltage. So the voltage across R2, R1, and the base here input voltage, it remains same. The input voltage Vin is constant. The voltage across R2, R1 is equal to the input voltage because all these three branches are in parallel. So now the voltage gain AV is given by output voltage divided by input voltage. Output voltage can also be written as output current multiplied by effective load resistance. Here the load resistance RL cannot be taken alone because the collector resistance is coming parallel with load resistance. So effective load resistance need to be taken. Similarly, the input current multiplied by input resistance. Okay, this we are writing it as IC RL dash. The effective load resistance is nothing but RC collector resistance is in parallel with the load resistance divided by the base current multiplied with input resistor. Here he has given specifically R1 resistor is given. Whenever two resistances come in parallel with each other, the effective resistance will be equal to the lowest resistance of these two. Okay, assume this is R1 and R2. The effective resistance, equivalent resistance will be equal to the lowest resistance. So here we are considering R1 is the lowest resistor because that value is given here. R2 value is not given. So we are assuming that R1 is the R1 is the resistance of lower value. So the effective load resistance effective equivalent resistance of R1 parallel with R2 is equal to R1. So here we are writing as R1. This IC divided by IB can be written as current gain, output current by input current. So AV is equals to the current gain AI multiplied by effective load resistance divided by R1. So if you substitute these values, AI is minus 49.32 divided by R1 is 1093 multiplied by RL dash effective load resistance, that is RC parallel with RL. So RC is 1 kilo ohm parallel with RL. So RCRL divided by RC plus RL. If you calculate this entire thing, the value will be minus 24.61. This is the voltage gain. So the answer is option A. We'll see the next problem. What is the collector current for CE configuration with a beta of 100 and base current of 30 microamps? So the collector current, so what is beta? The beta is nothing but an amplification factor of CE amplifier. For common emitter amplifier, the input current is base current, the output current is collector current. So output current IC divided by input current, that is the current amplification factor. So here beta is 100, IC is not given, IB is 30 microamperes. So if you calculate, IC is equals to 3 milliamps. So the answer is option B. So we'll see the next question. For an amplifier, which parameter is calculated with Vs is equals to 0? So this basically comes with the H parameters. If you consider CE amplifier common emitter configuration, this is base, this is emitter, and this is collector. Here the available voltage is VB, that is the input voltage, and here the output voltage will be VC, collector voltage. And input current is IB, base current, output current is IC, collector current. So if you write H parameters for this, input voltage VB is equals to HIE, that is the input impedance of the common emitter configuration, multiplied by IB plus HRE, that is a reverse voltage gain, multiplied by output voltage VC, collector voltage. Next equation, IC, output collector current, is equals to HFE, forward current gain, multiplied by IB plus HOE, output admittance, multiplied by VC. These are the equations. So he's telling we must make VS is equals to 0. Means the input voltage source should be 0. So why we have to make Vs is equals to 0? To turn IB into 0. That is input current should be made 0. By making IB equal to 0, you can find out these parameters, this HRE and HOE. Here, if you see carefully, you can find out HRE is equals to VB divided by VC. Next parameter is HOE, which is equals to IC divided by VC, which is nothing but admittance. Okay, so this admittance, if you make the reciprocal of this, that is nothing but output resistance. Output resistance is nothing but the reciprocal of admittance, output admittance. So by making Vs is equals to 0, we can turn IB input current to 0. By making input current to 0, you can find out two parameters, that is a reverse voltage gain. Second one is output admittance. In turn, you can find out output resistance also, because the reciprocal of admittance is nothing but resistance. So the answer is option B. We'll see the next question. An amplifier using a transistor has a voltage gain of 100. If the input voltage is of 65 millivolts, the output voltage is. So the voltage gain is nothing but output voltage divided by input voltage. Voltage gain is 100, given as 100. So he's asking the output voltage. The output voltage is nothing but AV multiplied by V in. That is 100 multiplied by 65 into 10 to the power of minus 3, which is equals to 6.5 volts. So the answer is option A. Next question. If alpha DC, that is alpha, current amplification factor for common base, alpha is equals to 0.99, IC, collector current is 6 milliamps, IC B0, that is the reverse saturation current of common base configuration, is 15 microamps. The value of IB is. We shall write the collector current equation. This is the common base. This is the common base configuration. Okay, this is emitter, this is base, and this is collector. So for common base configuration, IC is equals to alpha IE plus IC B naught. This is the equation. So the current collector current IC is equals to alpha multiplied by the emitter current is nothing but sum of base and collector currents plus IC B naught. Collector current value is given as 6 milliamps. Alpha is 0.99. The base current is not known to us. Collector current is again 6 milliamps. The reverse saturation current is 15 microamperes. So if you solve this, we'll get the base current IB as 45 microamperes. So the answer is option A. Coming to the next problem, what is the typical range of the output impedance of the common emitter configuration? So if you see this, we have to see the typical ranges of the common emitter configurations, but we'll see along with the common emitter, we'll see the common base and common collector also. Okay, typical values. So first comes input resistance. Input resistance, if you see, for common base, it is less than 100 ohms. For common emitter, it is about 750 ohms. For common collector, it is very, very high. The common collector, it is very, very high. That is 750 kilo ohms. Similarly, output resistance for common base, it is very high. The output resistance for the common base is very high. That is 450 kilo ohms. They may ask any kind of questions in the examination. They can ask common base, common collector, common emitter also. So for common collector, it is around 45 kilo ohms. Common emitter, it is 45 kilo ohms. Common collector, it is less than 50 ohms. So which of the following configuration has the least output resistance? Means the answer is common collector. That has the least output resistance. Next parameter, if you see the voltage gain. Voltage gain is for the common base, it is around 150. For the common emitter, it is around 500. For the common collector, it is less than 1. So these are the voltage gains. The configuration which has the unity voltage gain is nothing but CC, common collector. The answer will be. Next, if you see the applications. Common base is used in high frequency applications. That is RF applications. Whereas common emitter is used in audio frequency applications. Whereas the application of common collector is impedance matching. Common collector is mainly used for impedance matching. Because of its high input resistance and low output resistance, it is used as an impedance matching device. So now, what is the typical range of output impedance of common emitter? It is nothing but 45, means answer is option A, 40 to 50 kilo ohms. Like the video, share the video, and subscribe to the channel for better content and more videos. So next question. An ideal value of input resistance of trans resistance amplifier is. Here we'll see we have 4 types of amplifiers. The first one is voltage amplifier. Second one is current amplifier. Third one is trans resistance amplifier. Fourth one is trans conductance amplifier. Anything can be asked in the examination. We'll see these 4 amplifier parameters in detail. We have to write here output parameter, input parameter, output resistance, and input resistance. These are most frequently asked questions. For all these 4 amplifiers, anything can be asked in the examination. Output resistance of and input resistance of voltage amplifier, current amplifier, trans resistance, and trans conductance. Anything can be asked. So we shall see in great detail. For voltage amplifier, the output parameter is output voltage. Input parameter is also a voltage, input voltage. Output resistance for the voltage amplifier is very, very low. Ideally, it will be 0. Whereas the input resistance, it is very high. Ideally, it is infinite. Similarly, for the current amplifier, the output parameter is output current. Input parameter is also input current. That's why it is current amplifier. The output resistance of current amplifier is very high. Ideally infinite. and input resistance of current amplifier is low. Ideally, it is 0. For the trans resistance, the output parameter is voltage. The input parameter is current. That's why output by input, that is V by I, it is trans resistance. So the output resistance for the trans resistance amplifier is low, whereas input resistance it is low. Input resistance and output resistance both are low. For the trans conductance amplifier, the output parameter is current. Input parameter is voltage. The output and input resistance both will be high. So anything can be asked in the examination. Here he is asking ideal value of input resistance of trans resistance amplifier is. Input resistance of trans resistance is low. Ideally it is 0. Answer is option B. In order to operate, next question, in order to operate the C amplifier in the saturation region, which of the following conditions should be satisfied? This is very important. The collector current is equals to beta into IB. So basically the collector current depends on IB, base current. So the base current IB must be very high. The base current IB must be very high to drive the transistor into saturation region. So once the IC enters saturation region, IC becomes IC sat. Okay, is equals to beta into IB. So we are telling IB must be greater. It should be very, very high. So we have to write the IB should be greater. IB must be greater than IC sat divided by beta. So the answer is option B. The common collector transistor configuration used for impedance matching. We have already seen the common collector CC. The current gain is equals to output current is emitter current, input current is base current, whose current gain is very high, highest current gain. And voltage gain is approximately equal to 1, which has a high input impedance and low output impedance. So because of these parameters, it is used as an impedance matching device. The voltage gain of the amplifier stage is lowest in common collector. Why it is unity? See, if you see, this is emitter, this is resistance RE, this is collector RC, this is base. So if you observe carefully, this is the input current, base current, this is the output current, that is emitter current. Here the voltage will be applied. So if you apply Kirchhoff voltage law here in this loop, whatever the base voltage VB is there, the same comes and drops at the VE at the emitter. The voltage drop here at the base emitter junction is very negligible. That is 0.7 volts. That is negligible voltage. So emitter voltage is nothing but the base voltage minus 0.7 volts. 0.7 is negligible. So the emitter voltage approximately equals to base voltage. So for the common collector, output is taken across the emitter only. Output is taken across the emitter, whose voltage is equal to input voltage, that is base voltage. That's why input voltage and output voltage both are same. So the gain can be equated to 1. It is a unity gain amplifier. Among the CB, CC and CE configurations, which of the following has a low voltage gain? Again the same answer, CC, common collector configuration. In CE configuration of the transistor, the output voltage ampere characteristics is plotted as, see, for the CE common emitter, this is the configuration, this is RC, RE, and this is the base resistor, RB. This is the fixed bias method, VCC. The output VI characteristics are plotted. This is VCE. The output voltage is nothing but VCE. And output current is nothing but collector current. So output VI characteristics are plotted against VCE and IC with constant input current. Input current is nothing but base current. IB is 2 microamps, IB is 3 microamps. By varying the output voltage, output current IC, collector current is calculated, plotted for constant values of input current. Okay, these are the output characteristics. So it is IC versus VCE or VCE versus IC with IB constant. So the answer is option C. Sri Raghava Academy, online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.